Okay, so this is our last video on substitution for integrals for Math 1560, Calculus 1 at U of L for fall 2017. There are two ways to deal with definite integrals. Okay, so here's, we've got limits of integration. One approach, and this is one that a lot of people will stick with, is to say, I already know how to do substitution for indefinite integrals, and I know how to use indefinite integrals to evaluate definite integrals because the indefinite integral gives me my antiderivative. Once I have an antiderivative, second part of the fundamental theorem of calculus tells me how to evaluate my integral. I just have to plug in the two endpoints and compute the difference. Okay, so we can do that. Let's try it out here. So in this first one, we first do the indefinite integral. So we say, okay, ignore the definite integral for a while, and we come over here and we say, okay, so what do I have to do here? Well, what's U going to be? Again, I look for composition. When you see things in the denominator, a good chance is that the composition you want is it's whatever function is on the bottom composed with the reciprocal function. And so we say, okay, if I take the derivative of the bottom, is it sitting up on the top? Well, up to a constant, yes, because x cubed, the derivative for x cubed is going to involve x squared. So I'm going to let u equal 4x cubed plus 2. du is going to be 12x squared times dx, right? And so then I multiply both sides by 1 over 12 to just get the x squared dx on its own. So this becomes 1 over 12 integral of 1 over u times du. So I get 1 over 12 times the natural log of u plus c. So I get 1 over 12 times the natural log, absolute value, 4x cubed plus 2. Plus c, but any antiderivative will do, so we don't actually absolutely need the plus c if we know we're going to go on and do a definite integral, because we're going to be plugging in numbers anyway, and it's not going to matter if we have that plus c, it's going to cancel out when we subtract, right? So then we can say, alright, we've got our antiderivative, so now we simply plug in the limits. It's 1 over 12 times the natural log of 4 times 4 cubed plus 2. Right, I plug in the upper limit, minus 1 over 12 natural log of 4 times 1 cubed plus 2. We don't really, both of these terms are positive, so we don't really need the absolute value. So 1 over 12 times 4 times 4 cubed, 256 plus 2 more. Natural log of 258 minus 1 over 12 of natural log of 6. Okay, you can leave it at that. I mean, if you want to, you could simplify, right? You could simplify with properties of natural logs. The difference, you could write that as 258 over 6. So that's 1 over 12. 6 goes in, 4 plus 3 more times the natural log of 43. You can even bring the 12 in if you want, right? It is the natural log of the 12th root of 43, right? But we don't really care about the numbers. In fact, you could have stopped, at that first equal sign here. You could have stopped there. You don't necessarily have to do the arithmetic unless you really want to. Okay, for the second one, again, we look for our U-substitution. This time we see that we have sine raised to the 4th power, so the obvious choice is to take U equal to cos x, or sorry, sine x. Getting ahead of myself. Okay, why don't you want to erase? Alright, we'll do it this way. Okay. Interesting. What's going on here? Okay, now it's working again. So u is sine x du cos x dx, and so we say, okay, the integral of cos x sine 4x dx is the integral of u to the 4 du, which is 1 over 5 u to the 5, which is 1 over 5 times sine to the 5th x. And so then if we want to put our limits in, now that we have our antiderivative, we can say that's 1 over 5 times sine 5th pi over 2 minus 1 over 5 sine to the 5th of 0. And again, if you want to simplify, well, sine of 0 is 0, sine of pi over 2 is 1, and 1 to the 5th is still 1, 0 to the 5th is still 0. So we get 1 over 5 for that integral. Okay, so that's one way to tackle a definite integral, is first to do the indefinite integral and then plug in your limits. The other way that you can do it is to kind of do things directly and realize that, you know, when you're doing this substitution, it affects not only the function but also the limits. And so one way to kind of think about this is that you're starting over here, you've got kind of a copy of the real axis corresponding to the u variable. You've got another copy of the real axis over here corresponding to the x variable. X is running from C to D, right? And then you have this function g going this way, right? A, B. Actually, that's not right. It should be just g of a. Okay? And so you're actually starting over here. You're starting with the integral on this side, and what you want to do is you want to kind of use this function and bring everything back over here and hope that the integral on the left is a little bit easier. And so with something like this, we can say, okay, let's see. E to the 2x, I know that e to the 2x is e to the x squared. Okay, so I'm going to let u equal to e to the x. Okay, and when x is equal to 1, u is equal to e. When x is equal to 0, u is equal to 1. Okay, and so then what I do is I say that, what's du? Du is e to the x times dx. So this time what I'm going to do is I'm going to substitute everything. So the e to the x dx simply becomes du. 1 over, so 1 minus e to the 2x becomes 1 minus u squared under the square root. 1 minus u squared. And instead of my integral going from 0 to 1, now it goes from 1 to e. Okay. I did have it right the first time. Yeah. We kind of go back the other way. So a is equal to g of c. B is equal to g of d. Okay, and so now I can say, all right, well, what is the integral for 1 over square root of 1 plus u squared? Oh, that is arc sine. So this becomes arc sine of u. And now these limits are with respect to u, right? U equals e, u equals 1. And so I can just plug those in, the integral from 1 to e. And so I get arc sine of e minus arc sine of 1 as my definite integral. So this way you don't have to, this is another way to do it. You don't have to worry about substituting back. You can just substitute everything. So when you do your U-sub, you change the function, you also change the limits, the corresponding limits, right? And then you don't have to change back. Otherwise, I would have to get my arcsine of u, then I have to put in my u equals e to the x, and then I would plug in my original limits, right? So the other way I could have done it is if I had done it using the indirect approach, I would be doing arcsine of e to the x, and I would be evaluating from 0 to 1, and I would get the same result, right? I would plug in x equals 1, I would get arcsine of e, I would plug in x equals 0, I would get arcsine of 1. So same result either way. There are times where it does kind of, it can be advantageous to change your limits. Let's try a couple more just so we get a feel for how it works doing things this way. Okay, so here I look for a U-substitution. Well, the U-sub is a pretty obvious one, right? U is going to be this 4 plus 2x cubed. Du is going to have to be 6x squared times dx. So this is going to be 1/2, right? So I want 3x squared dx, right? 3x squared dx, so I need to divide by 2 to get 3x squared. 1/2, I'm going to put the limits in a bit. This just becomes u squared, the 3x squared times dx, right? That's my 1/2 times du. Okay, but now I also have to get my limits. So when x equals -1, u is going to be 4 plus 2 times -1 cubed. That's 2. When x equals 0, u is going to be 4 plus 2 times 0 cubed, which is 4. So now I have the integral from 2 to 4 of u squared du. And because I've changed my limits, I don't have to worry about substituting back. So antiderivative for u squared is 1 over 3u cubed. So 1/3 times 1/2, I get 1 over 6 u cubed from 2 to 4. So I get 4 cubed over 6 minus 2 cubed over 6. Alright, we can leave it like that. If you want to work out the numbers, you can, but I will leave it unsimplified. Okay, here's another one. The obvious substitution here, u equals cos x. Okay. Now, before we proceed, one of the things we might ask ourselves here is whether or not this integral actually makes any sense. Does this make any sense? It doesn't, because between minus pi and pi, I'm going to hit a couple of points where cosine is 0. All right. We'll go through the motions just to see what it looks like. But in fact, one of the things you might always be on the lookout for is that maybe the integral you've been handed doesn't actually exist, right? The fundamental theorem of calculus only applies if you know that the function you're dealing with is continuous between the two limits of integration. This function is not continuous between minus pi and pi. There are two vertical asymptotes. So the integral doesn't exist because the function is undefined at plus or minus pi over 2. So really there's nothing more that we should do here. We simply stop at that point. If we were going to continue, we might say, well, when x is equal to pi, u of pi is cos pi, which is -1. U at minus pi, cos of minus pi, is also -1. So let's say I had the same thing, but maybe this cos was up here in the numerator, so I didn't have to worry about this division by 0 problem. I just had sin x times cos x to the 4. Well, then there's also an interesting thing that happens, and this is one of the cases where it might be useful to look at your limits of integration when you substitute. Once again, there's no point in continuing on and doing the indefinite integral and going through all that steps of doing the substitution, getting the indefinite integral in terms of u, substituting back in terms of x, and then plugging in my limits, because we notice that when we change variables from x to u, the upper and lower limits end up being the same, and we know what the integral should be if the upper and lower limits are the same. If we were in a situation where that integral did actually exist, the integral would be 0. Right? So the limits are the same. The integral doesn't have a value. Well, it does have a value. That value is 0. So that's again something that you might want to watch out for. Okay, one last example, and then we'll call it a day. What do we do with this last integral? There is one obvious substitution, right? I do have a function under the square root. Under the square root, I have u equals x plus 1. Okay. du, though, what is du? du is simply dx. So now you might be worried or wondering, what do I do with this x out front? What do I do with this x? Well, if u equals x plus 1, that means that x is u minus 1. Subtract 1 from both sides. Okay. When x is equal to 0, notice that when x is 0, u has to be 1. When x is 1, u has to be 2. So where does this get me? Well, let's just plug everything in and we'll see what happens. So we get the integral from 1 to 2. X becomes u minus 1. Root of x plus 1 becomes root u. Well, the reason that this is better than what we had before is actually now I can multiply through the brackets, right? This is u to the 1/2. I can actually multiply through the brackets, simplify, and I'm going to have something that I can tackle using the power rule. U times root u is u to the 3 over 2. Minus 1 times root u, so u to the 1/2. I can do each of those using the power rule. The first one, I add 1 to my exponent. 3/2 plus 1 gives me 5/2. Then I need to divide by 5/2, so that's the same thing as multiplying by 2 over 5. Adding 1 to 1/2 gives me 3/2. Divide by 3/2, so I multiply by 2/3. And I evaluate between 1 and 2. So I get 2 over 5. I get 2 to the 5 over 2 minus 1, and then 2/3, and I get 2 to the 3 over 2 minus 1, and I'm done my integral. Alright, so after this we've only got one video to go. We've got one last topic to look at, which is calculating area between curves, and then we're going to be completely finished with the material for Math 1560 this semester.